Thanks for having me. So I'm very pleased to be here. I literally was in your seats 10 years ago. I went to PITP in 2003, so this is nice to come back and talk here. Now, as Nima alluded to, the LHC has finally started probing into new territory for Electroweak production compared to Lep2, which turned off more than 10 years ago. But the question is, why on earth do you need 2 lectures on this? And what exactly did the organizers want out of this? So, of course, it's always better to ask for forgiveness than permission. So I'm going to interpret what I'm going to do in my own particular way for what I think you might be interested in hearing. So the question is, when we talk about Electroweak production at the LHC, what are we actually talking about? Do we just specify some new representation? So let's say we have some extended gauge sector, and we happen to have, for instance, some new W prime gauge bosons that can be produced and they're charged. And we can produce them, for instance, through normal Drell-Yan processes with the gamma or Z. We make some W primes. These things can decay to leptons and neutrinos or to quarks, etc. You specify the representations of SU2 cross U1, you calculate the N. So why do you need 2 lectures to encompass all this? So what I'm going to hopefully giving you for the next 3 hours of talks, and only an hour and a half now because I know you have lunch after this, is that there's a number of key issues that are surrounding Electroweak physics that I hope we can address. So first off, the question is, why has the LHC entered the Electroweak era? And what exactly does it mean to enter the Electroweak era first off? Now obviously Lep2 shut down a long time ago, but there was this beautiful high energy physics program in the US called the Tevatron that unfortunately no longer exists for high energy physics. But why didn't that have any impact upon the Electroweak sector? As Nima said, we haven't had anything since Lep2. So I'm going to try to address this question, and it's an important question because it's not just simply, okay, you calculate the number here and you don't get enough events or something like that. It really has to do with the kind of different sorts of backgrounds associated with Electroweak physics compared to associated with just pure QCD physics. So I'll talk about that a little bit, and it looks like you were set up nicely between Nima's lectures and Michelangelo's lectures, so I'll try to zoom through a little bit of that. So that's the first starting question I really want to ask. The second thing about talking about entering the Electroweak era, now that we can probe states that have Electroweak quantum numbers, is what does this imply for Higgs and Electroweak symmetry breaking? So all of the fancy first limits that come out of the LHC that you probably saw immediately saying supersymmetry is dead or things like this, this is all based on particles that are in some sense tangentially related to the Electroweak symmetry breaking part of the standard model. Once you start probing quantum numbers that actually can be directly coupled in the Electroweak sector, then you can start having indirect implications. And there is a long history of going back and forth here in terms of whether we can talk about direct probes of the Electroweak sector, or we can talk about what are indirect probes if things couple to Electroweak symmetry breaking. So as Neil alluded to in one of the statements about a dark matter model, that there's a lot of Electroweak precision constraints on new physics. And so if something has Electroweak quantum numbers and it talks to Electroweak symmetry breaking, there start to be implications for the interplay between these 2 points of directly probing it at the LHC and also making sure everything is self-consistent. And then the last thing that I hope to emphasize is that it looks possibly, well, I'll put this as a question and then you can say it's no, but is something interesting going on in the Electroweak sector? And my answer to this is yes. I'll be talking about this more tomorrow. But since we've finally just been able to start probing the Electroweak sector beyond LEP, so beyond 100 GeV roughly, we are really having to test the standard model in new regimes that we've never tested it before at a precision level. And there are certain anomalies that are popping up, and I'll use that essentially as a case study to go through a number of these things. So today's lecture, I'm going to try to cover what's our current direct knowledge of the Electroweak sector in BSM. And I'll give a number of examples from some different models. I'll be talking about supersymmetry mostly, but I'll talk about a number of other things too. And then I'll try to start eating into this question a little bit here. What is the implications of direct searches for Electroweak imply for Higgs and Electroweak symmetry breaking and vice versa? Because even if you say that we found like the standard model Higgs and that's it, I'll also be emphasizing that how we actually experimentally search for Electroweak states and the production of Electroweak states can completely alter how we interpret the Higgs that we've seen, okay? You know all the signal strengths of the Higgs, so Scott's already given 2 lectures on the Higgs itself, but all the signal strengths of the Higgs are based on a particular way of doing a very data-driven approach to the Higgs, and if there are new Electroweak states right around the Electroweak scale, these 2 things can have lots of implications going back and forth for each other. So the starting point, let's talk about our direct knowledge of the Electroweak scale. So the Electroweak scale, we can essentially classify Electroweak states in 2 ways. Okay? So this is the first classification we'll give. We can either have states that are charged under U1Q, or we can have neutral states under charge, but it can still carry SU2 quantum numbers, similar to a Z. So the current state of the art from LEP, okay, we're going to do this in a historical fashion. So LEP1 and LEP2, so LEP1 was a Z-pole machine, LEP2 reached up to twice MW and then it went beyond it. And if we take a state that's charged under this U1Q, I'll call it chi plus minus, just have a nice supersymmetry flair to it. The rough bound on this is that this is the kinematic limit of LEP. Which turns out to be around that this m chi plus mass has to be greater than approximately 100 GeV. Okay. Now for experts in the audience, I'm going to make some statements that are very bold and very rough, and you know that there's caveats that are incorrect about what I'm going to make, but I'm going to modify these things and add the caveats in later, so you don't have to jump on me very immediately. For neutral particles, well, first off, they're much more difficult to produce. And the rough bound I'm going to give for a neutral particle, I'll call chi 0, is, I'll call it, if you have m chi 0, it needs to be greater than approximately mz over 2. Okay. Now this isn't actually true. This is just a rough kind of idea of where you start to have to worry. This comes from just the production of these charged particles. You can get up to 100 GeV. This starts coming from some of these indirect things that I'm talking about. How, if you have new light Electroweak states that can interact with the W's and Z's, you have to start worrying about indirect constraints on these. So for instance, like as I said, this comes from just producing this at an E plus E minus machine. We can make this chi plus, chi minus. Whereas this, for instance, we can think of as I make a Z, and this Z can decay into these chi 0 particles. So this would correspond to the so-called invisible width of the Z. Now, there's caveats to both of these statements, okay? The true statement about charged particles, okay, at LEP depends upon the actual charge of the particle, and it depends on exactly how it decays. Okay? So it turns out that you can have new charged states that can be as light as, for instance, order GeV. Okay? You can ask me how later, but that's a true statement. And we can also have neutral states that can be massless for all intents and purposes. But as with anything with model building, I mean, I kind of noticed it also from seeing Neil's list of dark matter models that he gave. If you've got anything from the lectures so far, a lot of model building you can just fool around with, and it essentially starts looking a little bit more and more like this, which you can't see from the contrast. But I saw it in Nadi's overview that he had a platonic solids model of this. This is from the Galileo Galilei Museum, and it's an armillary sphere, so it's an astrolabe, and these are supposed to be, the Earth is at the center of this, and there's all these intricate spheres around. So we can always do things, but this is the rough kind of knowledge that you have. So after LEP, we could have charged states had to be about 100 GeV. Neutral states, you can go all the way down to massless, but you have to depend upon what particular type of neutral state. If you're really coupling to the electroweak gauge boson strongly, then you have to start worrying once the thing gets under half the Z mass. Okay. So that's the current state of the art as of LEP. Now, I haven't talked in any detail about, for instance, how these particles decay. I just said you produce this thing. Okay, obviously, you don't necessarily see one of these chi plus or chi minus particles. If it's stable, that would be a very bad thing. You would have been ruled out cosmologically on many other grounds. And this, I said, these chi zero particles, okay, they could be stable, but they could also decay. Now, the point is that in a Lepton Collider, like LEP, you don't have to worry quite as much about how the thing decays. Okay, a Lepton Collider, you have a fixed center of mass energy. Okay, these E plus E minus beams come in, and you know everything about the initial state. So basically, you can capture all the information about the final state, and you can set pretty stringent bounds. Whatever you do with these decays, it's really hard to get away from this 100 GeV limit. This thing here, like I said, you can have ordered GeV states, but you start having to kind of stand on your head and then put some hula hoops around your arms in terms of the models and everything else. It's very hard to get down to this. Okay, so 100 GeV is a nice rough bound. At a Hadron Collider, though, things are a lot more difficult, and we need to care a lot more about how things decay. So if we talk about these electroweak states, we can have various production mechanisms, but we can also factorize this and look at some of the possible ways these things can decay. So if I think of a Hadron Collider as these protons coming in, and I'm going to be picking off some parton with inside the proton. So for instance, I can have a Q and a Q bar coming in. And then I'll have some hard matrix element that I'll denote as M. Now, the thing that comes out of it will be some electroweak state. Let's call these two particles phi 2 and phi 2. Just for the heck of it, I haven't associated any quantum numbers with these things so far. I'll just give them a name. Now, they have a number of different possibilities, and the bounds that we'll be able to put on these particles and how they'll interact with the rest of the electroweak symmetry breaking sector will depend on also how they decay. So one possibility is that they decay directly to the standard model. So for instance, I could have this phi 2 particle decaying just to a lepton and a neutrino. So kind of like a W, okay? So I have some new W-like particle that can decay. I could also have some sort of cascade decay where I have this phi 2 particle going along. It could spit out a lepton and go to some other particle, I'll call omega, then spit out a neutrino, and then go to some other particle, phi 1, and then eventually end up in the standard model, for instance, with QQ bar. Or I could have decays to another sector, which is the standard paradigm that you see everybody employ for now. And for instance, I could have this phi 2. It could decay through, for instance, a W gauge boson. And this W could decay then into a lepton neutrino, QQ bar, and then some stable phi 1 particle, so some stable neutral particle. And people like this paradigm because of, for instance, Neil's talks before, and I'll talk about it more tomorrow, that people can think of this as dark matter particle. But it's really not necessarily anything to do with dark matter. We don't have to concern ourselves with the relic density or whatnot. This is just a statement that there is some other sector It has some different quantum numbers associated with it, so that's why it ends up in that sector and doesn't decay down to the standard model. So from this perspective, we have a number of different choices, and we'd like to understand exactly how these different things manifested at a Hadron Collider and why they should give very different bounds. So the starting point is we need to put this picture into an equation and try to understand some rules of thumb for where the electroweak sector bounds should come from and when we should start caring about them. So the starting point for putting this picture into an equation is factorization. And if we have the total cross-section to produce PP goes to what I've called here as phi 2, phi 2. Okay. This is just the integral over dx1, dx2, fa of x1 at some q squared, fb of x2 at some q squared times sigma hat of ab going to phi 2 at some q squared. And that's our standard picture of the total cross-section factorization. And to something that depends upon this hard matrix element M, that's this sigma hat here, and our PDFs. So the question is, why do we care about electroweak production? How do we factorize that from talking about color production? What is the difference that's really going on here? So there are two things that matter, starting with the general formula for a cross-section at a Hadron Collider. So the first point is that the A and B partons can be gluons for strong production. Okay, so that's a possibility. But then again, it depends upon whether or not gluons are dominating for a given process. We could also have something initiated by QQ bar that could produce new colored particles just as well as producing electroweak particles. So there's the first question on what these partons are, when they're active and when they matter, so we'll look at that in a second. Then the second part of this is just the actual hard cross-section itself. Okay? But if I'm comparing color production to electroweak production, so that means I have to be starting with quarks over here, then the only thing that matters, since they have the same PDFs that I'm talking about quarks or for electroweak or quarks for color production, is just the factor of the gauge coupling essentially in the actual hard matrix element. So if I talk about colored production divided by electroweak production, this is just going to give me a factor of alpha s over alpha weak squared. And this gives me a factor of about 10 to the 2. Okay? Now, of course, there's caveats. There's color factors involved. There's exactly what the spins of all the particles. I'm comparing one model versus another model, etc. But this is the rough number. Alpha s at mz is 0.1. This is 10 to the minus 2. So there you get your factor of 100. So we'd like to try to quantify this and understand when we're going to get this factor of 100 and when this part can influence a little bit more. So the best way to describe this is through a so-called parton luminosity. Okay. Now, I don't know if this was specifically discussed by Michelangelo, but the basic idea is if I'm factorizing this to say I have a hard cross-section and some PDF sitting over here, I would like to say at a given q squared, okay, what's the amount of probability that I'm pulling off these quarks, okay, to have a cross-section normalized just by these PDFs out in front. So parton luminosity can be written in the following form. I can write dl dm squared as 1 over s, the integral from tau to 1 of dx over x, f1 of x, f2 of tau over x, and we define tau to be equal to m squared over s. So this is just saying I'm going to fix the given q squared, or m squared of the process, the center of mass of the actual hard process I'm talking about. If I'm talking about from that scale up, that's how much luminosity I have available to produce this. And if you go to any of the standard people that produce PDFs, you can find very nice plots of parton luminosity distributions. So this one is from Sterling. And you see here that this is for 3 different colliders, one at 8 TeV, one at 14 TeV, one at 33 TeV. Not surprisingly, these are LHC in mind numbers for what's past, what's going to come, and what possibly will be the future with a 33 TeV machine. And you see for the first part, if we're talking about whether we're dominated by quarks or for gluons and comparing electroweak and strong production, if I look at low center of mass energies, the gluon versus quark effect is very dominant. Okay? So if I look at the blue curves, which is the glue-glue PDF, glue-glue parton luminosity, it's dominating at the electroweak scale itself. Whereas if I start reaching high values, okay, if I have this crossover for 8 TeV at about 2 TeV, I see now all of a sudden QQ bar starts dominating. Okay? And that's just the standard thing, if I'm sure when they went over parton distribution functions, that you have all the C quarks and C gluons that are happening at low x. When you start to get out to high x, then you start being dominated by your valence quarks. So this can be an effect at low x's, okay? But as you start getting to moderate things and probing, for instance, new scales, then really what we see is that, okay, the quark PDFs are not that different from the gluon PDFs at high x's. So then the only thing that's left over really matters is about this factor of about 10 squared, okay, when I compare electroweak versus color production. So let's see if this actually holds true whatsoever. So we can take a particular example and try to see if this rule of thumb that I'm giving you here matters or not. And the particular example, instead of calling these things phi's and everything else, I'll look at supersymmetry. And the canonical example of how I compare colored versus electroweak, I'll look at the production of gluinos versus the production of winos. Okay? So I can calculate the production rate for either of these things. So this is an example where we just calculated for the Tevatron, the LHC, and 7 and 14 TeV. These are the NLO cross-sections from Prospino for a wino on the left and a gluino on the right. And we can see, let's take, for instance, the arbitrary point, which had the biggest tick mark, so that's where I drew my line through last night, of 500 GeV. Okay? And at 500 GeV, if we look at the Tevatron, so this is a pretty high X for the Tevatron. The Tevatron's a 2 TeV collider. Each beam is about a TeV. So we're talking about a very large X. If I look at the wino, okay, on this log-log plot, I intersect there at a little bit below the bottom dash line, whereas if I look at the gluino cross-section, I intersect a little bit below the second dash line at the top. This is, each one of these is a factor of 10, so you get exactly this factor of 100 that you see here. Okay, so at the same q squared, at the same m squared, when you're dominated by QQ bar PDFs, you're going to have this rough factor of 100. Okay, so physics works, nothing's fancy, we can use our factorization formula. Of course, the numerical factor of 100 or so is pretty big. Okay, looking on a plot, it looks like a gigantic factor. But we also have to keep in mind, because the PDFs themselves, if I look at the parton luminosity, all of these PDFs are falling like rocks. So if you have this factor of 100 that's going on between color production and electroweak production, that's not necessarily going to translate to saying that I can bound colored particles at a TeV, but I can only bound electroweak particles at order 100 GeV. So we'd like to understand a little bit more of what's going on and whether these rules of thumb work or not. So for instance, we can take and see how much, if we take the same cross-section, how much the wino versus the gluino depends upon this. And roughly a factor of 100 in the cross-section. If you take a factor of 100 in the cross-section, this turns into a change in the bounds of the masses. The bounds of the masses change by roughly 100 to 500 GeV. Okay? Again, this depends exactly on whether you're in different regimes for the PDFs, whether you're sitting in the C regime or you're sitting in the valence regime. But you're talking about a few hundred GeV that's going to be coming out by this factor of going from Electroweak production to color production. So one thing we can naively do is see how far the Tevatron should have got beyond LEP and understand whether or not this factor of 100 accounts for everything that we should have seen. Okay? So one thing we can do naively, so Sunil is going to talk later about how they actually do these experiments and set bounds. We can say, let's say we had a perfectly running experiment and we just had to have enough new physics events that we could see something. Okay? So the luminosity of the Tevatron ended up being around 10 inverse femtobarns. So Tevatron was about 10 inverse femtobarns. So what we could demand is that, okay, let's have at least 10 events. Okay? That's a good number. One event, probably we're not going to discover anything or set bounds that are going to be too strong. So let's demand a cross-section for new physics. That's 1 femtobarn. And if we take a 1 femtobarn cross-section, so that's the middle dashed line, so we can see that this turns out to be approximately, for a colored particle, this intersects, let's say, about 600 GeV. So mass of, let's call it our perspective gluino, is about 600 GeV, using this naive rule of thumb. And the mass of our Wino, if we go to a 1 femtobarn cross-section, okay, that's a little bit less than 500. Let's call that around 400 GeV. Okay. So this is what we naively get if we just accounted for the cross-section factors, the parton luminosities, and just stop there. If we just compared colored versus Electroweak, we'd have that colored things at the Tevatron should have gotten to 600 GeV. Winos, you should have got to 400 GeV. But as Nima said at the very beginning, we didn't actually go up compared to LEP. Okay? So the actual situation was the following. If we look at the Tevatron bounds at the end, and then Sunil can yell at me later because he worked on these things and maybe I'm misrepresenting it, but I'll add the caveats in later. If I look at the mass scale for Electroweak production versus colored production, this is 100 GeV. The bounds on Electroweak states ruled out this region, and this was from LEP. The colored particle states, when you turn on the Tevatron, they stayed exactly there. The Tevatron bounds didn't increase on LEP, and the colored particles went up to about 300 GeV. Okay, so this is the bound, for instance, on gluinos at the Tevatron. So our naive guess is a little bit off. Okay, I mean, we get 600 GeV for colored particles. It turned out to be 300 GeV. This was 400 GeV. It was 100 GeV. We'd like to understand what exactly is going wrong here with these estimates. Why did this happen? And to understand why this happened, we have to understand the various backgrounds that are going to be affecting colored particle production versus Electroweak particle production. So let's look at the topologies for the actual production of these particles and how they'd be seen at a Hadron Collider. So in the case of Electroweak production of Winos, so we can initiate this with a QQ bar. We can make a pair of Winos, which will make the charged version of these, for instance. And the charged version of these, because they're the partners of the W, can decay to a W, and then they can decay to the neutralino. So we have a final state of this that looks like, for instance, W plus, W minus, plus missing energy. Whereas the gluinos themselves have a background that looks like the following. I can make, for instance, using the same QQ bar PDFs, I can make gluinos that then decay through squarks and quarks. And a neutralino. Have the same thing on the top as on the bottom. So I'll have a state that looks like 4 jets plus missing energy. So the cross-section numbers themselves reflect the fact that I should have different bounds a priori between electroweak states and colored states, but I also have very different objects that are showing up in the collider. Here I'm having jets. Here I can have electroweak final states, for instance, gauge bosons. Now, we'd like to take, for instance, the colored case and understand why didn't we get up to this 600 GeV, but why did we get beyond LEP? So, what are some of the backgrounds to a 4-jet plus MET final state? Okay. So we're looking for other things that can generate this same objects in the standard model, but don't come from our gluinos themselves. So the first background, and the background that's hardest to understand, is just pure QCD. So I can make as many jets as I want, but of course, I don't necessarily measure all these jets perfectly. So the imbalance between the mismeasurements of these various jets can add to some amount of missing energy. And so QCD itself can be a background. The next biggest backgrounds that we care about are, for instance, making W's and Z bosons in addition to jets. So, for instance, if I make the W and it decays to a lepton and neutrino, I have actual missing energy coming from that neutrino. I don't have to just mismeasure stuff like in the case of QCD. And then I have an addition to jets. Depending on whether the study vetoes on leptons or not, I have to either lose the lepton or not. But this certainly is a background with jets plus missing energy. And the Z, if the Z decays to 2 neutrinos, this is also a background to jets plus MET. There's, of course, the possibility that I can just make TT bar production. Okay? Tops then decay into gauge bosons, W gauge bosons. Those can make missing energy, and I can also get jets out of this. And I can also just make dibosons. For instance, I could make ZZ production, where one of the Z's goes to jets, another goes to neutrinos, and lo and behold, I have jets plus MET. I can radiate a few extra jets, and if I get up to 4 jets if I want. So this is the backgrounds I have to worry about. These are the cross sections that we're interested in at the LHC, for instance, for electroweak and color production. So now what we'd like to do is look at what these actual background rates turn out to be. So some of you might have seen this plot. This plot was updated this summer by Sterling. And you see that the cross-sections that we're talking about were of order femtobarns. Okay, that's what we said. We wanted a femtobarn cross-section to get 10 events. Okay? This plot is in units of nanobarns on the right. So femtobarns are sitting way down here at the bottom, 10 to the minus 6. Every one of these backgrounds, starting with QCD, which we can think of more as almost the inclusive cross-section at the top, but really more think of that as the sigma jet cross-section. The W and Z cross-sections are order, not femtobarns, not even picobarns. These things are of order nanobarn cross-sections. Okay? So these cross-sections that we have to deal with as backgrounds are absolutely gigantic compared to the actual processes that we were talking about. So it's in some sense even a miracle that we could set bounds up to this high. Okay? So a 300 GeV gluino, if we refer back to here, has a cross-section that's sitting on the order of hundreds to thousands of femtobarns. Okay? Not anywhere near these cross-sections that we're talking about here. So if we want to keep these things in mind as a rule of thumb, I'll write down these cross-sections over here that we'll later refer to. Rough numbers that you can keep in your head for the LHC, okay, for 8 TeV or so, is the following. So sigma W and Z, which turn out to matter a heck of a lot. These things are order, let's call them 10 to the 3 to the 10 to the 5 picobarns. Sigma TT bar production, this is going to be order 10 squared picobarns. And sigma diboson will be of order 10 picobarns. Okay. So this is what we're fighting against. So what you have to do in any experiment, and as Sunil will talk about a lot more later in detail, is that we want to do two things here. When we're trying to set bounds on new physics or find new physics, we want to maximize our signal cross-section, but we want to also suppress our background cross-section. And this becomes a little bit difficult, of course. So we want sigma s to be high, whereas sigma b is low. And typically the way this is achieved is by going to certain kinematical regimes of the signal where the background becomes low. Okay? But in most cases, because PDFs fall in the same way for everyone, it's not always easy to do this. If I take the cross sections and I try to, for instance, probe in a regime where the standard model processes are going to be small, then I've also ruined all of my signal cross section. So this is a fine balancing act, and there isn't a very good, let's say, number on a rule of thumb for where this balances out at. This is the whole process of experimental physics, of how you optimize this to see the most reach that you can get. But the point is that the way that this is most easily accomplished, and the idea of supersymmetry, or most of the searches that are being done now, is for looking for larger mass scale separations. And the reason this is because the one handle both of these topologies have compared to the standard model is this extra missing energy. Okay? I put a missing energy, a dark matter particle at the bottom of this. So if I jack up the q squared of the whole process, that means that more momentum can end up being dumped into the neutralinos at the bottom. Okay? These standard model backgrounds that we list here, all their backgrounds are either from mismeasurement or from actual standard model missing energy that comes from neutrinos. Okay? These things have the characteristic scales of the W's or Z's unless I start boosting the W's or Z's by a lot. Okay? So if I can achieve a large mass scale separation, then I can knock down the backgrounds, but hopefully still have a little bit of signal left over. Now it turns out that for colored new physics, you just have the right amount of cross-section. This factor of 100 in the cross-section turns out to be I can take enough of a penalty on my signal and still see something. So this is reflected, for instance, in this CDF limit that was placed on squarks and gluinos. So this represents that rough rule of thumb number I just wrote down of 300 GeV. So in the plane of squarks and gluinos, LEP could reach 100 GeV, UA1 and UA2 were proton predecessors at CERN. And you see we have this contour that cuts in around 300 GeV. Of course, you also see this funny thing called no M-Sugro solution. This means that experimentalists, instead of thinking in mass eigenstates, said, hey, we're going to think of only one favorite theorist. And then you say, oh my gosh, what are they doing? Luckily, for your generation, all these face palms have mostly been avoided in the last 5 years. A lot of more interaction between theorists and experimentalists have prevented people from doing this. But this is why it's important to talk to experimentalists, okay? Or they'll literally make a plot where they hash that out, okay? At least the one dotted line from run 1 at the Tevatron, they actually put through the hashed area, but the hashing covers what they did for run 2. So you have to be careful and make sure to talk to your local experimentalists and make sure they understand to be as model independent. But like as I said, for your generation, luckily most of these issues have been avoided. So the 300 GeV kind of range that we are getting at, if we compare that to where this was on the gluino cross-section to see kind of the range that, of cross-sections we were talking about, this is about 10 to the 3 femtobarns, okay? So the gluinos, the Tevatron was able to probe to a cross-section a massive 300 GeV and a cross-section of order of picobarn. So gluinos can be ruled out at sigma of a picobarn and mass of 300 GeV. Okay? So we should go ahead and say, hey, maybe if we just go down and revise our estimates from instead of using a femtobarn as that number, that magical number I said to say 10 events, let's use a picobarn for electroweak states too and see what we have got there. Well, unfortunately, the Tevatron was just in the unlucky situation that if we go down to order a picobarn, okay, now we're sitting all the way back down here on the left-hand side of this Wino plot, and we're right at around the LEP limit of order 100 GeV, okay? So the Tevatron in some sense was just unlucky, Okay? The way the kinematics worked out, you couldn't really eke out more directly in the electroweak states. But there's one other problem that the Tevatron had and the LHC has, and as I'll talk about. And that's the fact that if we want to look at the actual 100 GeV scale, so that's where all the magic is. That's the W and Z, that's the Higgs, that's everything that could be associated with new electroweak physics. The problem is comparing this graph here with where gluinos are at a picovarn with this graph here, whereas winos are at 100 GeV. The point is the following. If the Q squared of the process, okay, if my root S hat of this is about 200 GeV to produce two of these particles, okay, the problem is the backgrounds to this Wino process, okay, the main background would just be a diboson topology where I'd have, for instance, two W's being produced. Okay, I'd produce QQ bar, I'd make two W gauge bosons, and they could decay, for instance, to a lepton neutrino, lepton and neutrino. Well, the problem is that the typical mass scale of this process, since I'm making real W's, is right around the same point. So the root S hat of this is about 2 MW. The problem, therefore, is that even if I could start bounding things from just looking at pure rates, the problem is the kinematics are going to start looking too similar. Okay? When the Tevatron had a 300 GeV bound, okay, it was sitting at 300 GeV. Sorry, the Q squared was that. So there was a separation between these various backgrounds and what the Tevatron could bite into. And this will come along a lot more in the LHC. So there's two effects. There's the cross-section effects, which do matter. There's that factor of 10 squared that you can keep as a rule of thumb if you want to compare the two. But there's also the fact that if I ever try to probe beyond the electroweak scale, I mean, if you build me a 33 TeV collider, I can easily jump up on this scale here. But if I'm stuck talking about the electroweak scale and I don't have a ton of luminosity or a ton of energy, I really have to start worrying more and more about my backgrounds carefully. Okay? So we can keep pinging on, but it's not that easy to go forwards. Now, the one way you can try to go forwards a little bit more with electroweak final states than for Wino final states is the following. I mean, I've just written this so far as essentially saying the backgrounds are exactly the same. I mean, in terms of these dibosons, etc. But the point is, if we talk about electroweak only states, the point is that if I can decay, for instance, into W and Z gauge bosons, or photons, etc., I can also generate leptons. And in fact, literally, Sunil is giving an entire talk on experimental new physics with leptons, so that's the point. So leptons let you get a lot better handle on things. Some of these backgrounds we don't have to worry about quite as much in terms of a QCD and W plus jets. You still have to be careful from them. And I don't want to slight the Tevatron entirely. Okay? The Tevatron did make some advancements. But the way you could start making headway is if you generate more leptons. Okay? So the standard model has ways to make leptons, for instance, with WW production and making leptons. Or I can make, for instance, WZ, and I can have 3 lepton events. Or I can make ZZ 4 lepton events. Okay? The problem, though, is if I'm talking about electroweak only new physics, if I'm making new W and Z gauge bosons that are decaying into leptons, okay, I pay the same branching fraction here to make those leptons as I pay over here with making these new standard model states. Okay? So I'm kind of stuck between a rock and a hard place of if I'm going to make these new electroweak final states, I can't exactly do it unless I have some kinematic separation, but how do I go back and forth there? So the one way the Tevatron was able to get around this was the following. Instead of looking at a spectrum where you have, for instance, Winos sitting at 1 mass scale, and then some other neutralinos sitting at the bottom of the spectrum here, and decaying through W or Z gauge bosons. One way the tevatron was able to set stronger bounds than LEP in certain regimes was if you actually put in new particles, for instance, leptons, in between the top of the spectrum and the bottom of the spectrum. Okay? Now, it's not going to actually generate topologies that look very different. So for instance, if I look at just the same sort of pair production of chargino-neutralino or pair production of charginos, then for instance, I can have a chargino coming in, a neutralino sitting on this side, and I can decay, for instance, to a lepton and a neutrino. And then this thing can then decay on further into a neutralino and something else. Or, I mean, it's really entirely up to my choice at this point here. But the point is, anytime I have, for instance, a lepton sitting around here, and if this lepton then decays into a lepton and a neutralino, this thing here does not have the same branching fraction as a W or a Z any longer. Okay? The branching fraction for a lepton into a lepton is going to be 100%. Okay? Now, there's different species. You can have mixing to other states or neutralinos later, but roughly the branching fraction can be easily order 1 compared to the branching fraction in the standard model where we're talking about order 10% for W's into a specific species, or we're talking about order a few percent for charged leptons of a specific species if we're talking about a Z decay. So the tevatron was able to set bounds better than LEP if I look at particular scenarios. Okay? For instance, if I put in a lepton partner. But you have to keep in mind that these things, again, I'm testing a given hypothesis. I'm not really testing whether I'm just generating new electroweak states and really just probing partners of the standard model. So in this case, you could go beyond the 300 GeV kind of paradigm, but I'll leave that up to Sunil to talk about later. So that's the state of the art as the tevatron. So let's jump ahead to the LHC and see why the LHC is interesting. Okay. So at the LHC, the picture in terms of the masses and electroweak states and colored states looks like the following. Okay? So we'll kind of do a snapshot as a function of integrated luminosity. So the first snapshot we'll do, okay, so here's our 100 GeV LEP scale. So the first kind of jump that we have here is that I can produce these things, okay, they're still at 100 GeV, but I run into the exact same problem when I have low luminosity. I'm producing W plus, W minus gauge bosons again. They have very similar kinematics. I can't really probe beyond LEP when the LHC first started. So for instance, if we take order 1 inverse femtobarn, electroweak states didn't really jump by a lot. Okay? However, all the headlines that you heard about when the LHC first turned on were that we saw no new physics immediately. The scale for new physics jumped up to 1 TeV very fast. Okay? And everybody started getting worried. And this is not a statement about supersymmetry. Okay? Talking about resonances, talking about anything else, 1 TeV was immediately the mark that came shooting out of the door when I talk about any colored new particle. So this was kind of the state of art around 1 inverse femtobarn. And then, of course, the next thing that happened at the LHC, you find the Higgs, and you say, okay, well, do I care or not about trying to say whether these states moved up at all? Okay? So you had a number of lectures by Natalia last week, and Nima also talked about naturalness, so hopefully you already have realized that it still matters to talk about these things. But from the perspective of setting given bounds, I really want to advocate supersymmetry when we're talking about electroweak versus colored particles or anything like this. Supersymmetry you can think of as a signal generator. Okay? We can talk about the naturalness problem and figure out how these things interplay into it, but we'd really like some sort of template where we can talk about am I producing new physics that has W's and Z's associated with it, and what's the scale that comes out of this? Okay? Now, the thing that next happened at the same point where the Higgs was found, so this is order 5 inverse femtobarns at 7 TeV, and then again 5 inverse femtobarns at 8 TeV. Secretly, at the same time that the Higgs was discovered and they were having all these press releases, something very interesting happened for the first time ever that went beyond LEP, as Nima alluded to. And it's the following, that if I have a given topology that looks like a pair production of a chargino and a neutralino in the following way. So I'm going to make this through some W that makes a chargino and a chi 20, so the second neutralino. If this chargino decays through a W into a neutralino 1, and the chi 20 decays through a Z gauge boson into a neutralino 1, then this bound, as I said, from LEP and from the Tevatron was 100 GeV, but you see the bound actually reaches all the way out to about 250 GeV now. So for the first time ever, at the same point that the Higgs is being discovered, so with the first 5 members femtobarn of the LHC at 7 TeV, you were able to actually set new bounds on electroweak physics. So why should you care? Okay? The Higgs is at 125. We've found no interesting signals beyond that. The reason is this relates to electroweak symmetry breaking potentially. Okay? When you're studying new colored particles, that's great. They may be associated with your model. They may be associated with naturalness, things like stops, etc. But what we're really interested in is the mechanism of electroweak symmetry breaking, the Higgs mechanism. Are there other new electroweak charged particles? So we would really like to probe this sector in a lot of detail. So even if you don't care about, for instance, this particular model, okay, for instance, for supersymmetry, we can write this exact same topology that they've just set bounds on in a completely different model. Okay? So for instance, a model that is a subsector of probably things Raman talked about last week is the following. We can talk about, for instance, a model based on an extended gauge sector that looks like the following. So let's say we have an SU2 cross U1 squared, for instance. And this SU2 cross U1 squared, we can have it broken at some scale, we'll call F, down to the diagonal, which will be the standard model electroweak. And then this thing will break through the normal Higgs mechanism to normal electromagnetism at low energies. Now, if we have this kind of simple setup, now this setup can show up in strong dynamics models. This can show up in things like little Higgs, which are kind of a pseudo-Goldstone model realization of electroweak symmetry breaking. The idea here is we have the same exact states as in supersymmetry if we go through this carefully. So here we'll have gauge bosons from both this SU2 cross U1 and the second SU2 cross U1. And so at a scale F, when this breaks down to SU2 cross U1, we'll have a set of heavy gauge bosons, and we'll have a set of massless gauge bosons, okay, which we'll call WH. So there's 3 of these guys, 1 of these guys that are heavy, and these things are exactly massless. Then when the Higgs mechanism occurs, the light ones will also get mass as well. But generically, if these 2 sectors are talking to one another through whatever dynamics is breaking this, etc., then these 2 sectors can mix. So these gauge bosons can mix. They can decay into each other. They can be produced from each other, etc. So an example topology that gives the exact same thing as charginos would look like the following. If I had, for instance, a pair production of a heavy set of gauge bosons, so let's call this WH, WH, okay, and I'll have it produced through some light Z, well, we'll call it Z or photon after we've identified the mass eigenstates. And if this heavy gauge boson decays, okay, it can create similar final states that we're interested in here. I could call this Z heavy also here if I want to make the same WZ final state we did for this. The point is we have 2 options. It can decay into the standard model directly. I can decay into leptons and neutrinos. Or it could, for instance, decay into the heavy gauge boson that was lighter than it, for instance, if there's a hierarchy between these two things, and it could spit out a regular W gauge boson. Okay, let's call it W light here. So the topologies are going to be the same, whether we're talking about things like little Higgs theories, extra dimensional theories, etc. If I'm talking about new electroweak states, LHC actually entered into this for the very first time. Now the reason why I prefer supersymmetry as a signal generator is that if you start playing around with alternative electroweak sectors, as I'm sure Raman talked about, you have to start worrying about the implications of these things for other measurements in the electroweak sector. So for instance, if I have new heavy gauge bosons that can mix with light gauge bosons after electroweak symmetry breaking occurs, then I have to start worrying about processes such as the following. If, just like when we set the original bounds on new particles coming from LEP, I said one of the dangerous things was the invisible width of a Z. So we can take, for instance, the Z gauge boson coming in. It can mix with a heavy gauge boson through the Higgs mechanism. I can turn into the heavy gauge bosons. So this would be a W3 heavy or an A heavy. And then this thing can decay and then into standard model particles. So for instance, L plus, L minus, or quarks or anything else. So if I have these new contributions of new gauge bosons that can mix with the standard model, that becomes a problem because now I have a new contribution to the Z width, just like I had when I had that new particle that the Z could decay into in the invisible width. So generically, the shifts on the Z width will look like the following. It'll start with something plus some coefficient for how strong these things mix, and it'll have an effect that's going as v squared over f squared, since the characteristic mass square of these guys will be f squared, and the mixing will be through the VEV of the Higgs. So I have to start worrying about these particular bounds. A similar bound, even if these things didn't directly couple to fermions, would be if I mixed a light gauge boson with a heavy gauge boson to shift the actual mass of the particle. So I can have a light one interacting through VEVs, and then I can have it switching back into a heavy and then switching back into a light. And this creates a shift in the actual W mass itself. So I'll have some delta MW squared over MW squared that'll have the exact same dependence. This will be some 1 plus CV squared over F squared, wherever C is the kind of constant I'm talking about. Now, why this matters is because these things have been measured very well at previous colliders before the LHC ever turned on. And the typical mass scales that come out of this is another kind of order 1 number if you have mixing between new heavy states and standard model gauge bosons, generic mixing, or new contributions to Z width. The masses of these new heavy gauge bosons will be order TeV if they're not protected by any additional symmetries or I'm not tuning things away. So this is immediately a reason why even if I have the same topologies, okay, I've generated the same topologies for WZ production using some new extended gauge sector compared to the supersymmetry, I'll end up with bounds that are much stronger coming from indirect measurements rather than direct measurements. Okay? So we have to be careful about how we include all these things. Now, since with 2 lectures I can't go into all these things, but I'll give a reference for this. This comes under the generic heading of electroweak precision tests. And a nice reference from this, I don't know if this is kind of forbidden at this school, but referring to another school. So you can look at Wittek Skiba's Tassi lectures on electroweak precision and effective field theory. And basically it comes down to the following, that if I introduce any new electroweak states that can communicate with the standard model electroweak states, I have to worry about the operators that I generate in the standard model after integrating out these heavy states. So for instance, there's a number of famous operators. We won't go through in any detail what these mean, but for instance, the T parameter, which I think Neil referenced before, is if you generate an operator that looks like the following. So if I have an H dagger d mu H squared, and this is a dimension 6 operator, so there's some scale sitting down here. So this will give me a contribution that'll shift the gauge boson masses once these Higgs fields acquire a VEV. So this is exactly the sort of scenario I have if I have integrated out these heavy gauge bosons sitting here. Okay? There are other contributions. For instance, there's a so-called S parameter, which is essentially some Higgs dagger, sigma Higgs, with a W mu nu. So this is the field strength for the W gauge boson in the standard model, and a B mu nu. And the point is, if I have any new electroweak states that can mix and generate these operators, I am normally in trouble much more than the direct bounds. Okay? This is the so-called little hierarchy problem, which I don't think I hear anybody refer to any longer because we're just also depressed about LHC results for the most part. But the basic idea is that if you look at these set of new electroweak states that could have shown up, the characteristic scale for this is 10 TeV, and we're probing things up at maybe a TeV scale in electroweak states from the LHC. So this also, though, is a lesson of why you can kind of look at the signal generation of supersymmetry. Okay? I'm not saying supersymmetry is the only game in town, but you typically need to ameliorate some of these problems associated with electroweak precision tests. So another thing that Neil referred to as a dark matter candidate, for instance, is putting on, for instance, a so-called T-parity, where you make these other states have some other quantum numbers, so you can immediately kill off any of these sort of mixing diagrams, and your life becomes a lot easier. Okay? Now, supersymmetry has a different mechanism for protecting this. It has the same gauge structure of the standard model, and you can't have a direct mixing of two different spins like I did there, but the basic lesson is the same. If you have some sort of symmetry that protects you against these things, you're golden, and then we can use the supersymmetry signal generations to go on for. So, I mean, examples of this, of showing how rigid these constraints are, kind of turning these operators, they restrict you into a very small oval, and changing this into units gives you order 10 TeV if I was going to plug in here. And of course, this is just two parameters. I also gave this example of if you have a Z-width sitting around here, if you have some new light electric particles that are going to screw up your Z-width, you also have to worry about, can I fit inside, for instance, that second one from the bottom? Can I fit inside the error bars for the Z-width or the invisible width itself? So you have to be careful about all of these things. And so SUSY is a pretty good signal generator for going on to these things. So if SUSY is a good signal generator, where do we stand? We'd like to kind of write out the basic numbers now and see how far we can push these and understand where they come from. So the rule of thumb for bounds on new states as of now is the following. If I have new electroweak states at the LHC, they have to be greater than approximately 300 GeV. And if I have new colored states, they need to be approximately greater than a TeV, as I said before. So this kind of sets a stage for where you can look for new physics. But do we really just stop here and we just keep incrementally pushing this on and on? So it's good to look a little bit more carefully about what these bounds actually mean. And CMS and Atlas always put out these really nice plots where they, I'm saying that a little bit sarcastically, where they put every single search they've ever done on the exact same slide. And you probably can't read any of these things, but basically it's just setting where the various different mass scales. So everything at the bottom of this are associated with direct electroweak production. So this is where we get kind of this 300 number. Everything at the top of this is coming from colored production through gluinos or squarks. And okay, that's fine. It's the total upper bound's about a TeV. As they say, probe up to the quoted mass in those small letters there. But this really doesn't give us any information. Have we really probed the electroweak scale up to 300 GeV? Are there any secrets lurking there? I always like to do this to my CMS friends, since I'm at Atlas and they don't have to worry. I kind of use this as a troll plot because it doesn't actually give us any information. It just kind of lumps everything into one thing, and we don't actually know the physics that's going on associated with this. It turns out, as I'm going to claim, that electroweak states can be right at 100 GeV. Now you can think back to my first comments of saying theorists can do anything. I can make a charge state all the way down in order GeV. But it turns out that this isn't actually much of a difficulty whatsoever. So the better way of, instead of looking at this summary of all these things, is to go into one of their individual kind of limit plots as a function of the kinematics. Okay? So this is a limit plot for direct electroweak production from CMS using the full data set. And what this is you're producing things through charginos and neutralinos, and you're decaying down to a lightest neutralino. But you can do it one of the two ways. You can do it through only electroweak gauge bosons, like I talked about why they haven't seen anything at the tevotron. Or you can do this through, for instance, leptons as well. Or we can talk about just direct lepton pair production. Now, the bound on new electroweak states, I said, was 300 GeV. That comes from this blue dotted line down here. Okay? So this blue dotted line here represents making chargino-neutralino associated production and having the branching fraction of these with the W and Z branching fractions 1. Okay? So you always decay to a W and Z on both sides of this decay. Okay? Now, that gets you bound up to about 300 GeV. If you stick in leptons, their branching fractions are different than W and Z's. You can push this way up. Okay? So the bound's much parametrically higher than 300 GeV. But the point is, if you look at the blue curve, you see the kinematics also are setting it in two different ways. One is being set from, if you go just on the right-hand direction on one of these plots, one of these limit plots, sometimes you see these with colors. I should have chosen one with colors. But the basic idea is if I'm going in this direction, I'm killing off the cross-section. Okay? I'm producing charginos and neutralinos. If I'm making them heavier, I'm not going to see them anymore. And that's fine. That's the expected direction. The other direction is this direction going diagonally, and that's associated with where the bottom of the spectrum is. So if I'm always decaying down to the bottom of the spectrum, if I start bringing the bottom of the spectrum up and up and up, then I start squeezing out the energy and momentum that these particles can come out with. Okay? So that's why you typically have all these things having this sort of shape. But you see there's kind of a very different shape dependence in terms of how far I can squeeze using, for instance, leptons versus how far I can squeeze when I'm talking about the W and Z. And the reason for this is the same reason, as I said, the tevotron kind of got into a problem with the W and Z and the WW new final states, is because you actually are producing actual W and Z gauge bosons. So you have to have a gap, for instance, to fit in a Z, okay, if you're decaying through a Z. And at the same time, if you want to set bounds, the typical way of setting bounds, as I said, is having a separate kinematic regime where the standard model isn't. Okay? So if you can't really get away from the standard model and have a good way to do some control region and a signal region, then you also run into difficulties. So you see relatively easily here, even though I can set bounds up to 300 GeV, as I start looking at this scale down here, okay, the production cross-section is still very high at order 100 GeV, but I start running out of kinematic discrimination to say whether or not I can say whether I have new physics or no new physics. So you can have electroweak states right at the electroweak scale. And this is really, from my perspective, one of the most interesting regions. Okay? There's implications here for Higgs physics. There's implications here for dark matter. There's implications here for baryogenesis. All sorts of things can go on right at this 100 GeV scale. The question is, how do we get into this scale? Whether there's anything going on, and how do we systematically treat this? Okay? So that's what I'm going to be talking about for the rest of kind of this lecture and the next lecture. And this slide, for instance, you see bounds have been set on W and Z, but we can do this a little bit more systematically, and that's what the experiments are starting to do, and we'll see updates on these. The way we can think about new electroweak states, not only is there cross-section, but we can think about categorizing based on the final state. So we had two different possibilities, one that it decayed into the standard model and one that it decayed into the standard model plus some other sector. I'm going to focus on the other sector category. So we can think of this just like the Standard Model does for producing electroweak particles. We can think of these as charge current final states and neutral current final states, essentially. So for instance, our WZ fits into our charge current description, and we have nice bound set on these. But the point is there's lots of other possibilities as well. So this bound can be set up to 300 GeV if I had the branching fraction into the W and Z where I branch into the Z 100% of the time. Okay? But if I'm talking about electroweak final state, it's quite possible that this neutralino 2 that's being produced and decaying down could also decay then into a W on one side and a Higgs on the other side. Okay? And accordingly, if I change the branching fraction, so I'm not decaying all the time into a Z, if I'm decaying a good fraction of the time into a Higgs, then that limit obviously changes quite a bit. And then I can also talk about, for instance, a W gamma final state. Okay? Not in exactly the same way, but you can come up with models that also have W gamma final states. The neutral current side of the thing, I can think of producing a pair of W plus W minus in the final state, okay, through normal Drell-Yan production. I can also think of producing other neutral final states. Now, these aren't really neutral current in the same sense, but I can think of producing, for instance, a ZZ final state, or a Higgs-Higgs final state, or gamma-gamma final state, etc. Okay, so these are kind of examples of how you can go through. So we're really starting to probe the electroweak sector in a lot more detail. We've gone beyond LEP for the first time, but we really still are in the infancy of trying to extract out all of this extra information. So W Higgs, for instance, is a very problematic final state because when I'm talking about Higgs, so I can look at this WZ1 and I can say, hey, let me have 3 leptons. That's a beautiful experimental signature, and Sunil will tell us all about trilepton signatures, and we can do that easily. When I talk about W Higgs, if I let the W go leptonically, well, the Higgs, that doesn't have lots of nice branching fractions in our favor, and okay, we can try to do these things, but the interesting thing is once we start probing these states here, for instance, this state, and this state, we start having to worry about another issue that I haven't touched on at all so far, which is, for instance, WH is what we normally think of as associated Higgs production. So I can search for the Higgs using gluon fusion, decaying to 2 photons, or I can do vector boson fusion. But associated production, where a Higgs stralung, that's also an important final state for looking for the Higgs. So for instance, when I look for eventually the Higgs to BB bar mode, if I'm ever going to get a nice signal in that channel, I'm looking to have a W that's having a lot of momentum to offset the Higgs, and I look for a boosted Higgs, etc. So new electroweak particles that populate these final states not only can affect the precision electroweak measurements, but they can affect the Higgs measurements by themselves. Okay? So this would generate associated Higgs production. Higgs to WW and Higgs to ZZ after Higgs to gamma gamma are the golden modes that we can find the Higgs in, Higgs to ZZ especially. Higgs to WW, it doesn't give you a good mass peak, as I'm sure you've heard about, but it is the 3rd most important channel for finding the Higgs. You got a lot of your signal significance coming from WW production. Okay? Now, the Higgs, of course, is not going to have the missing energy associated with these things. I said these things are all with the missing energy category as well. However, if I'm trying to probe the bottom side of this, the actual electroweak sector, okay, let's say I have some new particle that's order 100 GeV, and it decays to 2 Z's or decays to 2 W's, one on either side, then I'm not going to have a lot of missing energy associated with this particle. Okay? So I have to be very careful about what I'm doing. Well, you could say, well, don't the experimentalists have all this under control? There never could be any new physics hiding in this. I mean, I just have all the shapes of all my distributions, I do it, and that's the end. Well, of course, that's not actually the case. If you've heard about any of the Higgs channels of how they're looked for, all these things are done in a very data-driven manner. Okay? Now, despite theorists being able to calculate to next leading order and people also working on n cubed LO for Higgs processes, all the experimental understanding of the Higgs is still based on trying to do this in as data-driven way as possible. So, for instance, we can take an example where we look at the Higgs to WW final state. And the Higgs to WW final state is based on having a signal control region based on various different kinematical variables. So let's look at the L nu channel. And for instance, this one has a signal and control region, for instance, set up based on the invariant mass of the leptons of the dilepton system. There's other signal and control regions as well. But the point is that if I have new physics that also populates WW, and it doesn't have radically different kinematics, so it's just not thrown out by the normal Higgs to WW search, then if I talk about the number of background events in the control, if I talk about the number of events in the control region, and I talk about the number of events in the signal region, in the control region, I'll have the normal number of background events that would be in the control region. The idea is that the number of Higgs events in the control region is small. Okay, so we can think of this essentially as 0. It's not that in actual, but I'm doing everything rough here to give you an idea. But the point is that there could also be a number of events from new physics that are sitting inside the control region. Now, in the signal region, I have to figure out, okay, I have a certain number of Higgs events, and then I have a certain number of background events in the signal region, and there's a certain number of new physics events coming in my signal region. But the basic idea behind a data-driven approach is I am not going to just take this number for my background events in the signal region and just say this is what the n cubed LO prediction says, this is the number of events here. What's done is these control regions are set up, so I actually measure this, and then I rescale my background prediction to tell me what this number should be, the number of background events in the signal region. Okay? Now, that's perfectly fine if I have the right shape. Okay? If I have some kind of kinematic distribution as a function of MLL, and I have some background process that looks like this. So here's my background. And if I have kind of two different regions, one a control region, one a signal region, and if I just have this shape of the background that I'm just changing by an overall factor, this isn't going to mess up anything. This is just saying, okay, I have an overall k factor I screwed up on, and I'm fixing it by this data-driven method. Or I don't have to calculate the n cubed LO process or something like that. However, if I have some additional events sitting inside here from new physics that generates the same topology, like a WW or a ZZ or something like this, the problem is that what shows up in the control region and signal region does not have to have the same shape whatsoever. Now, if I had some new physics process that basically uniformly populated it like that, that'd be fine. But if I had some new physics process that essentially did this and then died off, then I would be scaling the background in the signal region incorrectly. I'd think I'd have a lot more background here, which would mean I'd have to scale up the number of background events in here, and I would get completely the wrong signal strength, because the signal strength for the Higgs that we're measuring in each of these channels is based on how much Higgs we think needs to contribute to this particular region. Okay? So this is another example where new electroweak states, although this is not something that we think about the first day we start talking about supersymmetry or something like this, can have drastic implications elsewhere. It matters for electroweak precision, and it can also change all of our interpretations. Okay? Everybody was excited, for instance, when certain signal strengths were greater than 1 for the diphotons originally at the LHC. Okay, those have normalized by a lot. But there's nothing telling us also that we don't have new physics sitting in things that are order 1 in the signal strength as well. Okay, we have to measure these things in a very sensible way. You could have artificially inflated or deflated certain signal strengths in these electroweak gauge boson final states. So these are kind of a number of the various issues that you have to be careful of. And of course, one of the other issues is if I have any of these new particles that are charged in generating these final states, these also can affect Higgs physics through, for instance, Higgs to gamma-gamma loops can be affected. Okay? If I have some new charged electroweak state running in a loop, I can change the Higgs to gamma-gamma rate. So there are so many different pieces of physics that are interplaying when we talk about electroweak final states, and you really have to figure out how to put all these things together. Now, obviously, I don't have a complete picture of this. No one has a complete picture of this yet. This is an active research direction. But there's a lot of different things, moving parts that we have to be able to take into account going on, and that's what I'm going to try to be giving you an example of. So this is kind of laying the kind of scenery out for what the different sorts of final states are. The ones that we've had a handle on so far that you've seen are the WZ final states, as I showed here. The WH final states, myself and collaborators, we set the first bound on this, but this is still probably not necessarily a strongly bounded channel because it looked like there was a fluctuation in the background. The one interesting one, and I'll leave you going to lunch with this one, is that there's a particularly interesting channel that I'll talk to you more about tomorrow, which is the WW channel that's been measured now 3 separate times, both at CMS at 7 TeV and at Atlas at 7 TeV, and at CMS at 8 TeV as well. And it looks very nice. You'd say, okay, everything fits pretty darn well, and nothing's going on here. All the data divided by predictions of order 1, you don't see any trends going on. And then this was the actual measurement of the cross-section. And you notice that CMS put this little thing in the very corner of their plot, that they were measuring the WW cross-section, but they did a data-driven normalization of the WW when they put it in here. Okay? If you're trying to measure the thing, you just measure the thing and you say that's it. You're not normalizing the actual thing you're trying to measure. So you'd think everything was fine, but then if you actually took out what their normalization is, this is what the actual WW measurement looks like currently at 8 TeV for CMS. And if you ever cared about new physics, which I'm sure most of you do, and you look at differential distributions a lot for new physics, for instance for supersymmetry or your favorite things, this thing doesn't look very well at all as far as a differential distribution. And in fact, the cross-section is off by about 20%. Now again, this is only a 2 sigma thing. I'll go into all the details of this tomorrow to give you as a case study for electroweak physics production. But there's something very interesting about this channel. It's been measured in a lot of different ways. A lot of different theoretical QCD calculations have been undergone in the last year or so to answer this, and all of them don't seem to fit the data, including the most recent one by Sally Dawson and others on a threshold resummation calculation. So there's an interesting story to be told here. This might all be just complete garbage, but I'll go through this as an example. But there's a lot of new physics in the electroweak sector, and this is really where you're going to expect all the bread and butter to be. You can care about pushing your gluino bound to 3 TeV or whatnot, but who knows whether gluinos or supersymmetry is the right thing. We really want to measure the electroweak sector because maybe it's something that Raman talked about last week. Maybe it's some strong dynamics or something like this. But whatever is associated with electroweak symmetry breaking is going to have electroweak quantum numbers, and you need to kind of cover this whole tableau of different final states. So I'll talk about this more on tomorrow afternoon. I'll go through this example, and we'll go from there. But this is an active direction, and there's lots of room for you guys to all go back after this and make some progress. So thanks.